Hey, welcome. Today, we're going to talk about the two families of elements that basically build, well, everything. Seriously, from the phone in your hand to the air you breathe, it all comes down to metals and nonmetals. So, let's get into it.
You've probably never thought much about it, right? But it's such a simple question, and the answer gets to the very heart of chemistry. Why is one material perfect for getting super hot while the other is designed to stop that heat cold? The whole secret is baked right into their elemental DNA. So, it turns out, pretty much every element you've ever heard of fits into one of these two giant groups. And it's their unique personalities, their properties, that decide everything: what we build with them, what we create, and really, how we live our lives. Okay, so, how can you spot the difference? Well, we're going to start with the easy stuff. The clues that are literally right there in front of our eyes, the things you can see and touch. First up, luster. It's just a fancy word for shininess. And metals? Oh, they are shiny. Think about a polished piece of silver or a chrome bumper. But nonmetals, like say a lump of coal, yeah, pretty dull. It's the first big obvious giveaway.
All right, next we have malleability. This is a huge reason metals are so darn useful. It just means you can hammer them into different shapes, like aluminum foil. They bend, they don't break. Now you try doing that to a nonmetal, like sulfur. Spoiler alert, it's just going to shatter into a million little pieces. Super brittle.
And this brings us right back to that cooking pan, doesn't it? Metals are fantastic at conducting heat and electricity. That's why your electrical wires are made of copper. And nonmetals, they're terrible at it. They're insulators, which is exactly why we wrap those copper wires in rubber to keep us safe.
Okay, so you're thinking, easy. Shiny and bendy equals metal. Dull and brittle equals nonmetal, right? Well, not so fast. Nature loves to break the rules. You've got mercury, a metal that's a liquid. You've got iodine, a nonmetal that's shiny. And then there's graphite, pencil lead, a nonmetal that actually conducts electricity. So yeah, just looking at them isn't going to cut it. We need a much deeper test.
To get the real story, we have to go beyond what we can see. We need to look at how these elements behave chemically. How do they react with other stuff? This is the ultimate identity test.
And here it is. This is the big one. When you react a metal with oxygen, think about magnesium burning with that bright white light, you get what's called a basic oxide. It's the chemical opposite of an acid. But when a nonmetal like sulfur burns, it creates an acidic oxide. That single chemical difference, that's the fundamental line in the sand that separates these two huge families.
But wait, it gets even more interesting. Even inside the metal family, not all metals are created equal. Some of them go absolutely wild, reacting with explosive force, while others are, well, they're pretty chill and barely react at all. So to make sense of all this, scientists came up with a ranking system.
And here it is, the reactivity series. Honestly, the best way to think about it is like a sports league table for metals. Up at the top of the league, you've got the superstars, the super reactive guys like potassium and sodium. In the mid-table, you've got your reliable players, your workhorses like iron. And way down at the bottom, you find the really calm, stable ones, like gold.
So, you might be looking at this chart thinking, okay, great, another chemistry table. So what? But trust me, this ranking is a huge deal. It has massive consequences for how we use every single one of these metals in the real world.
Let me show you. Potassium at the top is so reactive that if you expose it to air, it can just burst into flames. That's why it has to be stored in oil. Then you've got iron in the middle. Its reactivity is just right. It's strong enough for buildings and bridges, but it will slowly react with air and water. It rusts. And gold? It's at the very bottom. It's so unreactive that it basically never tarnishes, and that's exactly why we love it for jewelry. Okay, so we know how they behave, but where do we get them from? I mean, we don't just find pure iron bars lying around. Well, it turns out our knowledge of reactivity is the master key to the entire science of metallurgy, which is the awesome process of pulling these metals out of the earth. And it's basically a three-step recipe. Step 1, you gotta enrich the ore, which just means getting rid of all the useless dirt and rock. Step 2 is the magic part. You extract the actual metal from the compound it's trapped in. And step 3, you refine it, you purify it to get that shiny metal you're after.
And here's the kicker, the big aha moment. That reactivity series we just looked at, it tells us exactly how to do step 2. For the really reactive metals at the top, like aluminum, You need a ton of power, brute force electricity. For the metals in the middle, like iron, a simpler method works. Just heat them up with carbon. And for the lazy ones at the bottom, like mercury, you barely have to do anything. Just a little bit of heat and you're good to go.
But you know us humans, we're never satisfied with what nature just gives us. We figured out that by mixing metals together, or mixing metals with nonmetals, we can invent brand new materials that are even better.
This whole process is called alloying. And an alloy is basically a custom-designed material. It's a mixture that's specifically engineered to be stronger, or harder, or shinier, or just better than the stuff you started with.
You already know the most famous alloy on the planet, steel. Believe it or not, pure iron is actually pretty soft, but you add just a tiny bit of a non-metal, carbon, and boom, you've created steel, the super strong material that builds our entire world.
And it's the same deal with gold. Pure 24-karat gold is actually way too soft to make jewelry out of. It would bend and scratch constantly. So what do? We mix it with something like copper or silver. That alloy gives it the strength and durability it needs to last, and that's what 22-karat gold is.
And you might think this is all modern science, but it's not. Not at all. We've been getting really good at this stuff for a very, very long time. How long? Well, let me put it this way. There's a piece of evidence that's been standing out in the open for over 1,600 years.
I'm talking about the Iron Pillar of Delhi. This thing is a 6-ton masterpiece. It was forged more than 1,600 years ago. And here's the crazy part. Through some kind of masterful chemistry that we're still trying to fully understand, it has stood there through centuries of monsoon rains and blistering heat, and it has barely rusted. It's just incredible.
Think about that for a second. It's an absolutely mind-blowing achievement, and it leaves you wondering, right? If that's what we were capable of 1,600 years ago, what incredible new materials are we about to discover now? And what kind of world are they going to build?